All right, so what I did is it's problems, I think, 47 through 53. And we're just going to look at some example problems from the FE practice exam just to get a sense of what they're like. And then based on that, we can have a further discussion about these different things. So I guess I would say that something to watch out for on these problems is that the wording, you have to really read the wording and make sure you understand it carefully and don't allow yourself to get blown away by something that you haven't seen before. All right, so you can stop and think about this. So anyway, this is when a metal is cold worked, all the following generally occur except, all right? And this is a tricky question, all right? This is a good question, but it's a tricky one, all right? So we've got a couple different options, or 4 different options here. Recrystallization temperature decreases, ductility decreases, grains become equiaxed, and slip or twinning takes place, all right? So again, what is cold working?
Just strain hardening.
Strain hardening, all right? Beating on something, okay? So you're beating on this, typically, here it's a metal, all right? So we're telling us right here in the problem, we're take a metal and we're pounding on it, all right? So what would happen, all right? Could the recrystallization temperature go down as a result of that? Yeah. Huh?
No.
Tempting to say no, and it might be, so you'd say, okay, everything occurs except that, right? Boom, A, all right? Ductility decreases, right? Do work-hardened metals, are they more ductile or less ductile than they were before?
It's hardened and less ductile.
So is this, would ductility decreases be an accept? Okay, no. So we know the answer is not B. It might be A, but it's clearly not B. Grains become equiaxed, right? What does that mean? All right, well, we know what the equinox is, right? It's coming up. What is the equinox?
Middle.
Huh?
Equal on both sides, right?
Yeah, equi or equi means equal. All right, equinox means equal night, equal day and night. All right, first day of spring, 12 hours daylight, 12 hours of night. All right, but equiaxed, what does that mean? Axed.
Just equal axis.
Yeah, equal axis. All right. So by pounding on something, does that make would that make the grains equal in size and shape in all dimensions? No, pounding on something does what to the grains?
It causes jagged.
Yeah, it makes them distorted, right? Pounds them out, flattens them out. Okay, so clearly C is wrong, and it says slip or twinning takes place. Okay, we talked about why are metals ductile and ceramics are not, because what happens in the crystal structure of a metal that doesn't happen in a ceramic? The layers of atoms do what?
Slide.
They slide, all right? So cold working something, is that going to cause slip or twinning to occur?
Yeah.
Yeah, so clearly that's not the accept. So we've got it down to either A or C. Okay? Now notice we didn't just jump at the first answer, right? They put in what are called distractor answers, answers that sound very good, but they're not, okay? Now, taking a look at this, strictly speaking, all right, recrystallization temperature decreases, grains become equiaxed, all right? Now we have to think, all right? I can only pick one, all right? If I choose A, I'm saying that C must happen when you cold work something. Whereas if I choose C, I'm saying that A could happen. All right, so push comes to shove, what one is the better answer?
So isn't there an example where like mechanical properties versus chemical properties?
Exactly, yes.
Properties
Yep.
don't change depending on
Correct, absolutely. And that would, again, kind of steer you towards A, because recrystallization temperature is typically based on melting temperature, and melting temperature is a physical property, not a mechanical property. All right? However, all right, clearly C is wrong, right? And so in this particular case, C actually is the right answer. And you're saying, well, what gives here? This one had 2 right answers. The answer to the question is when you are doing work to something, when you're pounding on something, you are putting energy into the system, all right? You're putting strain energy into there. And so to get those distorted crystals to pop back loose, once you've distorted them, they actually do take a slightly less amount of energy because you've already put energy into them. So they do actually take a slightly less amount of energy to recrystallize than they would otherwise. All right. So this one, again, I'm going to have to kind of incorporate that into the 470 course a little bit. But in this case, the fact that you've got 2 wrong answers, an iffy answer and a no-brainer answer, you got to go for the no-brainer answer. All right. So this is FAST FE exam is as much about your decision making as much as it is about knowing the material. And so you have to have a good sense of being able to throw out the iffy answers and the no-brainer answers and find that one good answer. All right, and the correct answer is C. All right. All right, is this legible or not? These got scanned in, and I'm not sure that they're the best. All right, refer to the following chart. The temperature at which carbon has the same diffusivity in FCC iron as it has in HCP titanium is most nearly. All right, how would we do this one?
We have to go back to that equation.
Yeah, this is a plug and chugger, right? And we did these, right? I had you do, and this is why, right? Diffusion calculations, and it's that Arrhenius equation, that D0 e to the negative Q over RT. So basically, you got to go through, and they give you some options here. Okay. Now, when we work on this, what units are they using for temperature down here?
Celsius.
Yeah. What units are the Arrhenius equation in? Huh? It's D naught e to the negative Q over RT. That T there is in Kelvin. All right. So that's so you got to remember to convert these over, and I guarantee you, look at that. They put the 1200 and the 500. Those are about how many degrees apart? 300 degrees apart. All right. What's the difference between the Kelvin and the Celsius scale? 273, which is really close to 300. Okay. So they're notice how they're kind of catching you there. See that? You did give away that there's a distractor answer going on. Look at the other two, 8200 and 8500. What did they do again down there?
Same thing.
Right? Those pesky FE guys, all right? So basically, the difference between this and this and this and this is basically, can you do Kelvin or Celsius? And did you take the bait? So that's what they're really checking you there. So there's really, it looks like 4 answers, but there's really only 2. All right? And so it's either that one, somewhere around 1200, or somewhere around 8200. All right? And the only way to get past that, yeah, you got to plug and chug it. At that point, there's nothing left to do but to punt and calculate. So there you would have to do the nitty gritty. All right? And they show one way to do it here in these examples. All right, it's a D naught e to the negative Q over RT. Okay, so you're going to set the 2 D naughts equal to each other, and you're going to solve for T, and it shakes out to be about 1400 Kelvin, which is about 1200 Celsius. So there's your answer. All right, so eventually you get to the point where, yeah, there's no getting around doing a calculation, but again, just thinking about it carefully, you can narrow it down. You can say, okay, yeah, there's a couple different options here just by being smart about it. All right, so both this problem and the last problem, we were able to get it from a list of 4 down to 2. And that is a critical skill for passing this test. Right? At least you're doing a 50-50 guess, right? All right, the mechanical deformation of a material. above its recrystallization temperature is commonly known as? Working a material above its recrystallization temperature. Yeah, all right. So it's above, hot working, cold working, throw that out. Strain aging, grade growth, no. Hot working, all right? And this is just, you kind of have to know it. Right? Correct answer is A. Silver copper. I thought it was lead tin. All right. What kind of diagram is this? Do you remember?
Phase change.
It's a phase change diagram. All right. But is this a, remember all our different,
Eutectic table.
it's eutectic, all right? This is an example of a eutectic alloy, and then we have a eutectic point right there, all right? So, we have our phases, all right? Alpha and beta down here, beta plus liquid here, alpha plus liquid over here, a narrow alpha region coming down on the side, a narrow beta region coming down on the side here. Right? So they're saying silver copper binary diagram is shown below, the composition of a silver copper alloy that will be completely melted at the lowest temperature. All right, completely melted at the lowest temperature is. All right, and it's either 8% copper, 8.8% copper, 28.1% copper, or 71.9% copper. All right, and so what, all right, the alloy that has the lowest possible melting point, what percent copper is that going to be? Well, first off, where on the diagram am I talking about the lowest melting temperature? Yeah, right here at the eutectic point, right? So here's our liquid region, so here's my liquidus. And when the liquidus bottoms out, that is my eutectic point, right? At the bottom of the liquidus. Right? Now it's labeled 28.1, all right? But 28.1% what?
Copper.
Yeah, all right? So here's my copper from 0, 20, 40, 60, 80, and here's my silver, 100 silver, 80, 60, 40, all right? So clearly that's 28.8% copper, so the correct answer should be C. And did it right. Correct answer is C. All right? Yes. All right? Eutectic composition is when you got the lowest melting point, and that works out to be 28% copper. Now we've got silver and copper again. Same phase diagram, but this time they're telling us that it's 70% copper and is fully melted and allowed to cool slowly. What phases are present at 850 Celsius? All right, well, 70% copper. So, all right, on our axis down here, where are we going to be? Where? Right here, okay? So 70% copper. And we're going to heat it all the way up to all the way up here, and then cool to 850. So 850 will be right around here or so. And the question is, what phases are present? Beta plus liquid, right? And what is beta while we're at it?
Copper.
Beta is the copper phase. So we're going to have beta plus liquid. So it should be D, if I'm reading this correctly. All right. So at 850, beta plus liquid is present. And so sure enough, the correct answer is D.
If we did that for like 10%, it would be alpha plus liquid. Is the alpha in this example silver?
The alpha is silver. Yeah, you can see here's our 100% silver, and here's our alpha region coming down here. So the alpha is the pure silver. Yep. So at 10% copper, you would have a silver and a liquid copper type, a coppery type liquid. Right? It'd actually be a copper silver alloy.
And that's how we tell alpha beta with silver on the left on the alpha side.
Yeah, you have, because this is the 100%.
Right.
All right, this is the 100% silver here. So yeah, as we come down, alpha by inspection has to be the silver. Alrighty, a 40 millimeter bar of 4140 steel is quenched in an agitated oil bath. The expected RC hardness of the center of the bar is most nearly. All right, full disclosure, this is the one thing I did not teach you in 470, and so I created some slides to do this, to add it to the course, all right, but you didn't get it, so here we are, all right. Blah, 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 here's the explanation, all right. Rather than reading the fine print here, let me show you what's going on.
I'll make sure to cut all that out.
Huh?
I'll make sure to cut all that out of the video.
Cut what out of the video?
I didn't teach you that.
Why?
It would be entertaining.
Huh?
No, like you saying I didn't teach you that. I'll cut that out of the video.
Why would you cut that out of the video? All right, it's going to be in the video now. I didn't get to cover this in 470, all right? Should I walk right up to the camera and stare into it or something like that? Different alloys have what are called hardness curves, all right? And they're based on how deep the hardness, for lack of a better term, penetrates, all right? Slower pearlite formation is going to be equal to greater depth of hardness. So what am I talking about here? All right. Example of two TTT diagrams. We did see these. All right, here's your 1080. Your 1080, I got a pearlitic nose here. I've got to clear that pearlitic nose, and I've got to cool this thing down. I've got to clear that pearlitic nose in under a second if I want to form martensite. So if I want to harden that stuff up, it had better hit there and it had better cool down pretty fast. All right. On the other hand, all right, this is 4340 over here. Here I've alloyed the 4340 with chrome, molybdenum. I think it's got some nickel in it as well. All those things conspire to push our pearlitic nose way over here to the right. When I push the pearlitic nose to the right, I form a bayonetic nose, but even that bayonetic nose is at over 10 seconds, right? So I've got a lot more time to cool down the 4340 than I do the 1080, right? If I cool that down, all right, so what that means now is if I've got a chunk of metal and I try to cool it down, I'm going to be able to form more martensite over here than I will over there because I've got more time to play with. All right? All right? And the reason for this is that because steel cools from the outside in. So if I have a big chunk of steel and I'm cooling this side, the coolness, if you will, is going to penetrate into the material. And if I can get that coolness to penetrate, I'm removing heat, but think about it as the coolness moving in. If I can get that coolness to get in, anywhere that's at least below 1,000 by the 1 second mark, that will harden. And anything that's not below 1,000 Fahrenheit by the 1 second mark won't, all right? Now for flat plate, it's easy. For bar stock, it's not so simple because what's going on with bar stock is something like this, all right? I've got, not only is it losing heat at the ends, but it's losing heat on the sides and the other end and everything else. So what's going to happen is I'm going to have a hot core and I'm going to have cool all the way around it. These things lose heat faster than this does, all right? So if you did, remember the Jomny end quench experiment? You should have done it. You pulled that pin out of the furnace and you put it in a special thing with the water squirting on it from before. That's because the water's only hitting it on the end. That's very close to this situation because you're only cooling the end. Whereas if you actually plunge the whole thing into water, now I'm cooling it on the sides as well. All right? So here's how you do that. All right? You have to have what are called hardenability curves, and you have to also have knowledge of what's called the Jomny distance. The hardenability curves look like this. All right? So for something like a 1020 steel, all right, I will be lucky to get a little bit of hardness, and if I do have that hardness, by the time I get to the 1/4 inch mark or so, 5 millimeters, basically I've lost any hardness that I could possibly get. right? If I go to like a 1040 or even a 1060 steel, then you can see it again, I got a little bit more depth, but not much more. If I go to an alloy steel, 4340, 4140, now here, because those things take so much longer, there the depth of hardness, it can penetrate much deeper into the material. Right? Now again, this diagram here is for this case, all right? So this diagram, that diagram I was just showing you, this is like, case hardening some big casting or something like that. Whereas basically 1D heat transfer in from the sides, and you got a big warm area in the middle. However, if I'm working with bar stock or something like that, then I've got, now the heat transfer on the sides and ends starts becoming significant. And because the heat transfer on the sides and ends are significant, I need to calculate what's called the equivalent Jominy distance. And the way that this works, and this slide here somehow got, I don't know what's going on with the, there, that's better. All right, so that's the center. There's halfway. There's 3/4 of the radius. This is the mid-radius, so center, mid-radius, 3/4 radius, surface. That's how that's read. All right, and then you take a look at these things here. So we've got center, mid-radius, 3/4 radius, surface. And so what you do is you got to look up the bar diameter, and then you got to find its equivalent distance. And then you read down to find the equivalent distance, and then based on that equivalent distance, you then come over here and you look up the hardness. I'm going to do another example here for you so you can see that clearly. All right? So I've got a fully austenized 40 millimeter round stock of 1060, and we're going to quench it in water. Find that hardness at a distance 10 millimeters below the surface. All right? So again, the amateur error would be to simply take a look at my hardenability curve and say, hey, you want 10 millimeters? No problem, I'll do 10 millimeters, all right? And I'll just look up and it's 1060. So hey, my hardness is going to be about, 33 or so, 32. Okay, so there's my depth. There's my hardness. Looks like about 32, okay? Amateur error, okay? The right way to do it is, again, to say, all right, what's the Jominy distance? Since it's round stock, and we're talking is what, 40 millimeters in diameter, which means a 20 millimeter radius, and we're looking at a distance 10 millimeters below the surface. We're looking at the mid-radius curve here. Okay, so we're going to come up here. We're going to come up to a diameter of 40. All right, we're going to read across. I've got the lines here. Okay, so there's my 40 diameter. There's my, I'm going to be at the mid-radius curve. All right, so the mid-radius curve reads down to only 6 millimeters. All right, so what this means here is that for a round stock, a 10 millimeter deep into a round stock, it acts like it's only 6 millimeters deep. And the reason it acts like it's only 6 millimeters is because in the big casting, you're only getting heat on the surface. Whereas in the round stock, you're getting the heat transfer all around, so the round stock cools faster. So even though it's 10 millimeters deep, it hardens like it's only 6 millimeters deep. All right? So now that I know the equivalent Jominy distance, 6 millimeters, I now go back to this thing, and I'm going to use what Jominy distance? 6 millimeters, because it behaves like it's 6 millimeters. So I'm going to go to my 6 millimeter spot. I'm going to read up. Then I'm going to read across. And sure enough, the right answer in this case for my problem would be about 45. Right? So you can apply a similar process to the problem we just did. And then based on that, you're going to be able to see that we get the right answer. All right? All right. Problem 53, I didn't scan these, so I apologize for that. This one somehow got cut off, so this is going to be an easy one, right? It's just a coin toss. All right, so I don't know what options C and D are. This is a minimum crimp connector is used to connect a copper wire to a battery. What would you expect to happen? And the options that we can see are A, only the copper will corrode, or B, only the aluminum connector will corrode. All right, now I don't know what the other options are, but we should be able to get out a galvanic table and we'll see that aluminum is anodic to copper. All right, what is anodic? When something is anodic to something else, what does that mean?
Doesn't it corrodes faster?
Exactly, right? Anodic means it gives up the electrons, right? So you're going to think of the phrase sacrificial anode. That thing you're putting down inside the hot water heater, that is a sacrificial anode. It's giving up electrons. So aluminum is, again, highly reactive. It's high up near the top of the galvanic series, all right? Copper, anytime you see anything with copper in there, copper, gold, platinum, those things are way down at the bottom, okay? So just by looking at this, even without the galvanic series, all right, aluminum's anodic to copper. The aluminum is going to give up the electrons. The aluminum is going to be the one that's going to be forming, the oxide and doing those kind of things. So aluminum, in this situation, I would anticipate aluminum would be the one to corrode away.